Welcome back. So let me remind you that we were discussing redshift, very high redshift, when the temperature of the universe is more than 10 to the power 10 Kelvin. At that epoch, we have the electrons and the positrons, the neutrinos and antineutrinos, and the photons all in thermal equilibrium. So let me draw a picture of this. So we have the a part of the universe over here, where we have all of these. So we have the photon, electron, positron, neutrino and antineutrino, all in thermal equilibrium, and they are described by their respective occupation numbers, and we can work out what the contribution to the energy density from each of these is, and this is at a temperature more than 10 to the power 10 Kelvin, 10 to the 10 Kelvin. Okay. Then what happens as the universe expands? The universe cools, and at some temperature around 10 to the 10 Kelvin, the first thing that happens is that the neutrinos go out of thermal equilibrium. The neutrinos are weakly interacting particles, and for equilibrium to be there, the particles, all of these particles, have to interact with each other. But the neutrinos, they are weakly interacting, so the neutrinos go out of equilibrium, and so at some temperature of the order of 10 to the power 10 Kelvin, we still have the electron, but the neutrinos are out of thermal equilibrium. So the neutrinos do not interact with the rest of the material, and their occupation number is now frozen. So subsequent to this, all that happens is that their occupation number remains frozen. The frequencies change due to the expansion of the universe. So the universe, as far as the neutrinos are concerned, the universe is transparent somewhere over here at a much higher. The neutrinos become transparent somewhere here, 10 to the power 10 Kelvin. The universe is not transparent to the photons, okay, but the universe becomes transparent to the neutrinos, and once the universe becomes transparent to the neutrinos, we know how the thing evolves. Okay, the distribution function is unchanged. Okay, so here the neutrinos, so basically what happens here is neutrinos decouple because their scattering cross sections are much smaller. They are weakly interacting particles. Okay, now once the neutrinos have decoupled, again this thing has now two kinds of things. There are the electrons, which are the photons, which have adequate energy to maintain the electron positron pairs in thermal equilibrium. As the universe cools slightly more, so at a slightly lower temperature, what happens? The electrons and positrons also recombine. So the same thing, you only have the the photons and the electrons and the neutrinos and neutrinos. The electrons and positrons, they recombine. The temperature of the photon, CMBR, is not hot enough to maintain the electron positron pairs. It falls below the rest mass of the electron positron, and the electrons and positrons, they annihilate. So this is called pair annihilation, electron positron. The pair annihilate. Okay, the pairs annihilate, and you are left with just the photons. There is a small residual amount of electrons and baryons left, which scatters the photons and keeps them still in thermal equilibrium. Okay, small amount of baryon left, which is adequate to scatter the photons and maintain them in thermal equilibrium. The neutrinos have decoupled. Okay. So you see that there is the excess energy, the energy which was earlier there in this has now gone into the photons. There is a fair, okay, electron positron annihilation has occurred, and the energy which was there in the electrons and positrons here has gone into the photons. Okay. So you see that in this process something happens to the photon, the CMBR, which does not occur to the neutrinos. The neutrinos have decoupled. So this energy which was there in the electrons and positrons does not get distributed amongst the photons and the neutrinos. The neutrino is decoupled. Okay. So let us see what happens over here. So the temperature, let us assume that this happens at a temperature T. So the electrons, all of these species were in thermal equilibrium here. Even when they go out of equilibrium, the temperature of all of them scale in exactly the same way as inverse of the scale factor. So even here the photons, electron, positron and the neutrinos have the same temperature. Once you have the electron positron annihilation, the temperature of the photon will become different. So let us assume that the photons here have a temperature T gamma and the neutrinos have a temperature T nu. Okay. The conserved quantity is the entropy. The expansion of the universe is adiabatic. So the conserved quantity is the entropy. So let us assume, okay, let us now analyze how these temperatures are related. Okay. The entropy per unit volume, so let us ask what is the entropy of this. The entropy of this will have two parts. One part will be in the electrons and the photon which are interacting, electron, positron and photon gas which is interacting. So that to start with, the entropy of this, entropy we have already calculated, it is 4/3 internal energy by T. So the entropy of this to start with is going to be S is equal to S into V, which is 4/3 AB by T, and we have three kinds of particles. We have the photons. For photons it is T to the power 4, plus we have the electrons and the positrons which are fermions, right, fermions. For each fermion, each kind of fermion, the internal energy is 7/8 that of the photon. So this will be 14 by 6, 14 by 8 or 14 by 8. So this is the entropy of the volume of this. In this volume, this is V is the volume of corresponding to this, due to the photons and electron positron pairs. Okay. This will be equal to the entropy in the photons alone at the later instant after the recombination. So after the recombination, this will be equal to 4/3 AB by T, T photon to the power 4 into V prime, where V prime, this volume also would have changed due to the expansion of the universe. This is V and this is V prime. Okay, so we are here analyzing this part which initially had photons, electron, positron. After the annihilation it has only photons. the conserved quantity in adiabatic expansion is the entropy, so the entropy is going to be same, okay, before the annihilation and after the annihilation. Let us now also consider the neutrinos. The entropy of the neutrinos, again we can calculate in the same way. It is 4/3 AB by T, and we have so we have 7 by 8. We have, let us take one kind of neutrinos. Neutrinos do not have two polarization, they only have a single polarization, but there is a neutrino and the antineutrino. So again we will have 14 by 8. 14 by 8 can be written as 7 by 4. So this is 7 by 4 T to the power 4. So before this annihilation they are at the same temperature. After the annihilation this will be equal to into V. After the annihilation this will be equal to 4/3 AB 7 by 4 T neutrino cube into V prime. Okay, this is after the annihilation. The annihilation process does not affect the neutrinos because they are decoupled. They do not know that the electron-positron pairs have annihilated. The energy does not get transferred to the neutrinos. So the entropy in the neutrinos is going to be conserved, whereas the entropy in the electron-positron pair has gone into the photons. Okay, the total entropy is conserved. So we have these two relations. This is before annihilation, after annihilation, after annihilation. So from this we can just straight away eliminate these things, and what do we get? So let us look at the left hand side of this equation. The left hand side of this equation tells us that T gamma cube is equal to T gamma cube into V prime is equal to, so this is 7 by 4, so this is 11 by 4 T cube. Okay, 11 by 4, 7 by 4 plus 1 is 11 by 4, so 11 by 4 T cube V. For the neutrinos, V prime so what we see from this is that the neutrino temperature is equal to or so this is the final result. So what we have here is, let me recapitulate what we have learnt. So we, at temperatures more than 10 to the power 10 Kelvin, the CMBR photons are adequately hot, the universe is adequately hot, so that all of these things are in thermal equilibrium. Then the neutrinos go out of thermal equilibrium because their interaction rates are very weak, so they just free stream, and then what happens is that the electron-positron pairs annihilate, and the electron-positron annihilation pumps in extra energy into the photons, and though the neutrinos and the photons started off with the same temperature, the photon temperature gets jacked up by a factor which is 4 by 11 to the power 1/3 relative to the neutrino temperature. Okay, 11 by 4 to the power 1/3. So now after that both of these evolve in exactly the same way subsequent to this. They scale as 1 by a. So the present universe has a photon background, with a thermal spectrum at 2.736 Kelvin. In addition to this, there is also a thermal neutrino background which has a temperature which is equal to, whose present temperature is equal to 1.95 Kelvin, which is a relic of the hot past of the universe when the two were in thermal equilibrium. Okay, so the fact that you see a CMBR, cosmic microwave background radiation, at 2.735 Kelvin also implies that there is a neutrino background with temperature 1.15 Kelvin, 1.95 Kelvin. Okay, this neutrino background is very difficult to detect and it has not been detected. It is unlikely that it will be detected because the neutrinos are very weakly interacting particles, and any neutrino, the number density of neutrinos, so the number density of neutrinos corresponding to this, you can calculate that this comes out to be 3 by 11 times the number density of photons for this particular case, because the photon temperature is also higher. So this and this comes out to be 113 centimeter minus 3 z cube. Okay, this also will have a factor of 1 plus z, which I have not written. Okay, into. So these are the this is the number density of neutrinos, and such a neutrino, small neutrino, the number density cannot be detected by and large because the neutrinos are weakly interacting particles. Any detector here, these particles, the probability of detection would be extremely small. Okay, though the number densities are comparable to those of the photons, they are much weaker interacting, much weaker they have a much weaker interaction. Okay, so assuming that the neutrinos are relativistic, so we know of two distinct backgrounds of relativistic particles. One is the photons and other is the neutrinos. So we can now estimate the total density in relativistic particles at present. And this will be equal to 1 plus the number of neutrino families, number of flavors of families of neutrino, into 7 by 8 into, that is the, so given a neutrino of temperature T, its contribution to the energy density is 7 by 8 times smaller, into T neutrino by T photon to the power 4, which this ratio we have just calculated. It is 4 by 11 into omega gamma naught. Okay, this ratio we just calculated, it is 4 by 11. So this is the total energy density of relativistic particles in terms of the energy density contribution to the energy density from the photons, which we have calculated right in the beginning of today's class. So if you assume that the number of neutrino families is 3, so you have the mu neutrino, the electron neutrino, and the tau neutrino. These are the three kinds which are known to exist at present. So if you put in 3 here for n, then this comes out to be (1.68 omega gamma naught), and this is 4.22 into 10 to the power minus 5 h minus 2. Okay, so this is the total contribution from relativistic particles to the present energy density, matter density of the universe. Okay. With this, let us now go back to our understanding of the dynamics of the universe. So if you consider the dynamics of the universe, let me remind you again that the equation, the basic equation that we wrote down was h square t is equal to h naught square into, so I will have omega relativistic particles, and with the expansion of the universe, the contribution from the relativistic particles goes down as a to the power minus 4 plus omega matter naught a minus 3 plus other terms. So I could have curvature and cosmological constant, which will have smaller, which will have larger powers of a. So if I go to high and higher redshifts, we see that there will be a transition. The dynamics of the universe will forget about curvature and cosmological constant. Okay. Okay, we can put in a cosmological constant also. Let us assume that the curvature doesn't exist, 0. Okay. Now at scale factor of order unity, the nearby universe, that is redshift 0, the first two terms, the radiation, contribution from radiation is going to be much smaller than the other terms. So we can as well forget about this, because this we have seen is of the order of 10 to the power minus 5. The contribution from relativistic particles, which is often referred to as radiation, is of the order of 10 to the power minus 5, whereas omega matter and omega lambda are of order unity. So when the scale factor is of order unity, this can be ignored. So for the part of the universe where we see galaxies and other sources, supernova, etc., we do not have to bother about the contribution of the radiation to the dynamics. It is negligible. But if you go to higher and higher redshifts, then there will be an epoch when this term will by far outweigh these two terms. Okay, there will be a transition where the radiation, the relativistic particles, dominate the universe. So we shall have a transition from a matter dominated universe to a radiation relativistic particle dominated universe. So let us estimate where this transition occurs. So at A, if A is much smaller than 1, it is the first term omega r naught a minus 4, because it has a to the power minus 4, is going to be much greater than omega matter naught a minus 3. And we can forget about the matter and the cosmological constant. So let us see where there will be a transition between these two. So the transition will occur at the epoch where omega r naught a minus 4 is equal to omega matter naught a minus 3, or a is equal to or 1 plus z, sorry, other way around. Which is also equal to 1 plus z. Okay. So, we know the values, we have now values for this. So, let us put this in. So, this will give us that this will occur at redshift of approximately 4 point, so this is 0.3 divided by that's the omega matter, and divided by 4.22 10 to the power minus 5. I can take this h square on top. Okay, and so this is of the order of tens of thousands. At a redshift of around 10,000, the universe has a transition to a radiation dominated. So, this is where this is called Z equality. Okay. So, the universe, as you go to, so at redshifts greater than the redshift of matter radiation equality, the universe is dominated by radiation. And we do not have to bother about the matter part or the cosmological constant. So, the early universe is radiation dominated by relativistic particles. Let us also work out the solution at those times. So, the evolution of the scale factor at those epochs is given by A dot by A is equal to H naught square root of omega r naught a minus 2. So, this is dA. I can write this as dA by dt, and if I take this onto the other side, I will get a square, one of the a will cancel out. So, I have dA, a dA is equal to h naught or a square is equal to 2 h naught So, the scale factor goes as t to the power half during the radiation dominated epoch. So, at a redshift of more than around 10,000 or a scale factor or at a values less than 10 to the power minus 4 somewhere over there, at this is the evolution of the universe. Okay, this is how it evolves. And we also know that the temperature and the scale factor are inversely related, So we can straight away relate this to the temperature. So the temperature and the age are also related. So the scale factor can be written as the we know that T into A equal to 2.736. So so we can now express this as the temperature. So given the age of the universe, we can directly convert it to the temperature. Okay. So let me stop over here. I shall resume on this in can I take an extra class? I'll need one. It will be good if I can take one extra class. Monday afternoon, Tuesday afternoon, labs are open. And welcome to today's lecture. Let me remind you that we have been discussing the thermal history of the universe. And at temperatures, let me just go back a little. So at temperatures greater than 10 to the power 12 Kelvin, we have the neutrons and antineutrons, protons, antiprotons, muons, antimuons, and we have the neutrinos, antineutrinos, photons, electrons, and positrons, all in thermal equilibrium at these very high temperatures, 10 to the power 12 Kelvin. To put things in context, the temperature of the universe, the temperature of the CMBR at present is 2.725 Kelvin. So we are discussing really the early universe where it is extremely hot, and you have all of these species in thermal equilibrium. That this is just to remind you. Well, we are actually not interested in this epoch. If you go to lower temperatures, the neutron and antineutron, proton and antiproton, the muons, they all recombine. Once the temperature falls below their rest masses, the respective rest masses, they all annihilate, and we are here interested, going to start from an epoch that is where the discussion has been mainly the temperature scale of around greater than 10 to the power 11 Kelvin, but lower than the temperatures mentioned earlier. So this is where we start. At these temperatures, we have got the neutrinos of which there are three kinds, three flavors. Electron, the mu neutrino and the tau neutrino, all three of them, and we have the electron and the positron, and the photons, all of these in thermal equilibrium, and we also have some residual baryons. Small quantities, all at thermal equilibrium. So this is the epoch 1 that we are going to discuss today, and we have discussed earlier also. So this is the first phase of the universe that we are going to discuss today, and we have the second phase. So the universe is expanding, and as the universe expands it cools, and subsequent to this the temperature this is phase 2. Here as the universe cools, the neutrinos decouple. So nu and nu bar, they decouple from the rest of the material. They stop interacting with the rest. These are weakly interacting particles, and they stop interacting with the rest of the particles at a temperature T of around 10 to the power 10 Kelvin, and subsequent to this the temperature falls below the rest mass of the electron positron pair. So the electrons and the positrons, they annihilate dumping whatever excess energy they had into the CMBR, into the photons. So there is extra energy that goes into the photons at around 9 into 10 to the power 5 Kelvin. We have studied this, and as a consequence of this, what happens is that the photon energy T gamma is more than the neutrino energy. The neutrinos have decoupled, so they as the universe expands, the neutrinos free stream, and the temperature of the neutrino just scales inversely with the expansion of the universe. And but the photons also do the same thing till 5 into 10 to the power sorry, it is 5 into 10 to the power 9 Kelvin, somewhere around here, where the electron positrons annihilate, dumping extra energy into the photons. So the photon temperature goes up relative to the neutrino temperature at this epoch, and this ratio, we have worked this out in earlier class. It is 11 by 4 to the power 1/3, and this ratio is 1.401. We have worked out all of these things in the last class. So the neutrino temperature after this, after 5 into 10 to the power 9 Kelvin, is less than the photon temperature, and the neutrino temperature at present is 2.725 Kelvin divided by 1.401, which turns out to be 1.945 Kelvin. And this continues. So the neutrino, at present we have a photon background which we see as the cosmic microwave background radiation at a temperature of 2.725 Kelvin, and we also have a neutrino background at 1.945 Kelvin. So this is the situation. So once the electron positrons and positrons annihilate, we are left with a neutrino background and a photon background, both of which more or less just the temperature of both of which are different, and it continues to scale inversely as the scale factor till the present. And at present we have both these backgrounds, the photon background and the neutrino background. So we have discussed all of these things in somewhat great detail in previous classes. Today let us ask the question, how does the universe expand during these two different epochs. One is at temperatures before the electron positron pair annihilate. So, at temperatures more than 5 into 10 to the power 9 Kelvin, and second, how does the universe expand, what is the expansion rate of the universe, how does it expand at temperatures below this. This is the question that we are going to work out in today's class to start with. So, let us embark upon this. So, let us set out with this phase. So, we are going to set out with this phase where we have all of these species in thermal equilibrium. So, the total energy density of the universe rho, total energy density rho is equal to the energy density of the photons plus the energy density of the electron positron pairs plus the energy density of all the neutrino, 3 different flavors of neutrinos. So, this is what we would like to calculate, and we have already discussed this to some extent. Let me go through this again. So, let us first start off with the photons. So, we know that the energy density of the photon rho gamma is equal to the Stefan-Boltzmann constant AB T gamma, which is they are all at the same temperature. So, there is no need to distinguish between the different temperatures. So, the photon energy density is the Stefan-Boltzmann constant into temperature to the power 4, and to convert this into energy density we need to divide it by C square. And so, this is the energy density of bosons essentially with 2 spins. Photons we know have 2 spins. So, the energy density of a species of bosons with 0 chemical potential, 2 spins, is given by this, which is exactly what these photons are. Similarly, if you have fermions, let me remind you that if you have fermions, so then with these are bosons, and if you have fermions, two spins, then the energy density is slightly different. The energy density is down by a factor of 7 by 8. So, this is for fermions in thermal equilibrium at a temperature T, the energy density of fermions. So, this is the mass density, and assuming that the fermions have 2 different spins. So, we have the electrons we know have 2 different spins. So, for the electrons the energy density, for the electrons the energy density is given by this much. For the positrons also the energy density is given by the same thing. Both electrons and positrons have 2 spins each. So, we have 2 times 7 by 8 AB T to the power 4 by C square for the electrons and positrons. Let us now take up the neutrinos. The neutrinos only have a single spin. So, neutrinos have only 1 spin, and but there are the neutrinos and the antineutrinos. So, that is a factor of that compensates for there being only a single spin, and we have 3 flavors of neutrinos. So, the contribution from the neutrinos, assuming that they are massless, is 3 into 7 by 8 AB T to the power 4 by C square. So, we have worked out all the contributions. The electrons, we have electron and positron, which is why we have a factor of 2 here, both of which have 2 spins. For neutrinos there are 3 flavors. then we have the neutrino and the antineutrino, but only one spin, which is why we just have a factor of 3 over here. So, the total energy density is, let us calculate the total energy density. The total energy density rho is equal to 1 plus 2 plus 3 7 by 8 Stephen Boltzmann constant T to the power 4 by c square, and this is equal to 43 by 8. So, this is 5 times 7, 35 plus 8, that is 43 by 8. So, the total energy density is 43 by 8 times the Stephen Boltzmann constant by c square T to the power 4. So, that is the total energy density during this epoch at temperatures greater than 10 to the power 10, around 5 times 10 to the power 9 Kelvin. This is the okay. So, with this, let me also give you the value of the Stephen Boltzmann constant. The Stephen Boltzmann constant AB has a value 7.56 into 10 to the power minus 16 joules per meter cube per Kelvin to the power 4. What we require here is not the energy density, but the mass density, which can be calculated if we use the Stephen Boltzmann constant by c square, and so you have to divide this by c square 9 times 10 to the power 16, that is what you have to divide with, and what you get is then 8.4 into 10 to the power minus 33 kg per meter cube per Kelvin to the power 4. So, this is what we will use to calculate AB by c square, the energy density in terms of the temperature, and it will give us the energy density in units of kg per meter cube. So, we will use this now to calculate the expansion rate of our universe in this epoch. So, let us now put this into the expression for the dynamics of the universe. So, this will take us a few lectures back. If you recollect, we had worked out